Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome to this video where we are going to learn electron motion in the presence of magnetic field. Earlier, the last video it was for the formulation of motion equations for electron in the presence of electric field. Before that, we are introduced to what exactly the microwave frequencies are, the definition of the microwave we have known, the various microwave devices we have been introduced. We have also the knowledge of microwave systems, various applications in this microwave engineering, the units of measure also we have covered. So let us begin with the equations to see the motion of electron in the presence of magnetic field. When the magnetic field is present, so in that situation, whatever the force has been exerted onto the charged particle in the presence of that particular magnetic field is actually directly proportional to the velocity of that moving charge. It is also directly proportional to the magnitude of the magnetic flux of that particular magnetic field. It is also directly proportional to the sine of the angle theta. The theta is the angle between the velocity direction of motion of the charged particle, in our case it will be the electron here, and the direction of magnetic flux lines. So having this particular knowledge, we can have the formulation for the force exerted. So F, we can write F is equal to the relation with respect to the magnitude of the charged particle will also be there. So it is also directly proportional. Hence we take F is equal to Q into the velocity into the magnitude of magnetic flux into the sine theta. As we know that for the two vector quantities, if it is the cross product A bar cross of B bar, we have the formulation the magnitude of first vector into magnitude of second vector into sine of the angle theta between them along with the direction given by a n cap. The n designates the normal direction, that is the perpendicular direction to the plane in which these two vectors are present. Hence finally this particular equation relating to the force, we can write F is equal to capital Q V cross of capital P, because velocity and that of the magnetic flux, these both are the vector quantities and force is of course the vector quantity. Now we can replace Q by E as we have electron motion in the presence of magnetic field. Hence we write the equation F bar is equal to minus E V cross of capital B bar. So here we have to take the negative direction as the charged particle is the electron here. Now in above equation we have the cross product of velocity V bar into the magnetic flux B bar. So for cross product, if we have the two vectors A bar, so expressed into the rectangular coordinate system AX cap, then AY cap added with AZ cap. Similarly, we can have B bar expressed as BX cap plus BY cap plus BZ cap. The cross product A bar cross of B bar we can formulate with the help of this determinant. The first row will be having the unit vectors AX cap, AY cap, AZ cap. The second row will be having the coefficients of vector A, AX, AY, AZ, and the third row will be having the coefficients of vector B. In that case it will be BX, BY and BZ. So accordingly, as we are having the cross product with respect to the velocity vector V and that of the magnetic flux density B, for velocity vector, as we have V bar here, we can denote dx by dt into AX cap added with dy by dt into AY cap added with dz by dt into az cap. So this is actually the rate of change of distance with respect to the time here. So the distance change with respect to the x direction, with respect to the y direction, with respect to the z direction when derivated with respect to the time. So this is nothing but the velocity component in the direction of x. So along with the unit vector ax cap we can express here. So by formulating such a determinant along with the b bar expressed into the bx ax cap, by ay cap, bz az cap into the rectangular coordinate system, we can have the three equations denoting the motion of electron in the presence of magnetic. So the first equation, it will be d2x divided by dt square, it equal to minus e divided by m. In the bracket here we have bz into dy by dt. So this component you can also express as v suffix y, the velocity component in the direction of y, minus it will be having by dz by dt here. Now let us say this is equation number 1. The another equation, so this is actually the acceleration with respect to the x direction, so d2x upon dt square. The next equation will be representing d2y divided by dt square. So this is equal to minus the ratio E by m, charge of the electron divided by mass of the electron. In the bracket we shall be having bx into dz by dt, z component of the velocity vector, minus it will be having bz into dx by dt. This is the second equation, let us say. And the third acceleration component, that is d2z divided by dt square, can be shown as minus e divided by m. In the bracket here we have by dx upon dt minus bx, it will be dy upon dt. So as in the previous topic we have expressed the three equations into the rectangular coordinate system showing the motion of electron into the presence of electric field. These are the three equations for motion of electron in the presence of magnetic field. So here also there may be a need that the expression of the equation should be into the cylindrical coordinate system depending on the shape of the microwave device. Hence we switch from rectangular coordinate system to that of the cylindrical coordinate system. In cylindrical coordinate system, the cross product of the velocity with that of the magnetic flux density b bar, we can express v bar cross of b bar. So it will be given by, here we have bz into rho into v phi. You can also express a d phi upon dt to this particular component, minus we have b phi component in multiplication with the vz, that you can also express as dz upon dt. So this will be in multiplication to the a rho cap here, plus we can have capital B rho is the suffix here, so b rho vz minus bz into v rho component into a phi cap, and we can have b phi v rho minus b rho into v phi in multiplication with az cap. So taking into consideration this particular cross product, we can have the equation of motion into the cylindrical coordinate system. So the first equation I write here, it will be actually d2 rho divided by dt square minus rho times it will be d phi upon a dt bracket square, given by minus the ratio of charge of electron E to that of the mass of electron m. In the bracket here we have bz into rho into d phi upon a dt minus b phi times dz divided by dt. The second equation we can write, this will be 1 upon rho ddt of, here we have rho square in multiplication to the d phi by dt. So if you apply this ddt inside this bracket, it will be d2 phi upon dt square. This is the acceleration of the electron in the presence of magnetic field in the phi direction. So this was with respect to the rho direction, radially outward. This is with respect to the phi direction, angular direction. So it will be given by, here we have minus E divided by m in the bracket. It will be b rho dz by dt minus bz, it will be d rho by dt. And the last equation we can write, it will be the same kind of equation as we have z component here, but with some changes we can express d2z by dt square, it equal to minus E by m. In the bracket we have b phi component in multiplication with d rho by dt minus b rho into d phi by dt. So if we have named equations 1, 2, 3 for the earlier case into the rectangular coordinate system, this will be equation number 4, this will be equation number 5, and this will be equation number 6. So I outline this set of equations denoting the motion of electron in the presence of magnetic field. Now we have seen the three equations, first of all into the rectangular coordinate system, then into the cylindrical coordinate system, expressing the motion. Actually the d2, let us say x divided by dt square, this is the representation of acceleration. So acceleration into xyz components, and then for cylindrical components, that is rho phi z, we have shown. But how actually the motion will be there, that we can see or we can clear with the help of one diagram. So in this diagram, let us take the help of x-axis and that of the y-axis. So y-axis and x-axis are mutually perpendicular to each other. Now we have gone through the two set of equations, first of all into the rectangular coordinate system, then into the cylindrical coordinate system. The components that denoted the motion of electron, these were first of all, for example, d2x upon dt square. This is the acceleration component in the x direction. Similarly, we have d2y upon dt square, d2z upon dt square, and correspondingly d2 rho upon dt square, that is for the cylindrical component. Then d2 pi upon dt square, that we can take from the second equation from the last set, and d2z upon dz square. But to look at this particular mathematical equation, it is quite unclear how exactly the electron will be having a motion. I make it clear that the motion of the electron in the presence of constant magnetic field will be actually of circular fashion. So this will be better described with the help of one diagram. So in this diagram, we shall be taking the help of two axes, capital X and capital Y, which are mutually perpendicular to each other. So let us see the diagram. In this diagram, this is the x-axis, this is the y-axis, and the intersection point is the origin here. Now the third direction that will be actually perpendicular to this particular plane, it will be either coming outward from the plane or going inward into this particular page. So that is the third direction. Z direction we can take. So this direction we can take to denote the presence of magnetic field. This is inside the page, and for denoting the magnetic field we have the vector b bar here, magnetic flux density. Now if certain electron enters into the presence of this particular magnetic field, so very first of all we can denote its particular velocity. So the velocity of the electron, we assume v bar denoted as vx into ax cap. So we have assumed that x is the initial direction of motion of electron before entering into the magnetic field. Now for the magnetic field, we have already denoted into the diagram. So the magnetic field, we can write B bar will be having the component that is perpendicular to the plane of the paper. It will be BZ into AZ cap. Now when this magnetic field is exerting a force onto the electron, so that time the force of interaction here F bar, it will be actually minus E into the V cross product V bar with that of the B bar. So if you take the cross product into the account, the cross product is giving us the resultant direction that is perpendicular to the plane of the two vectors that are contained into that particular plane. So the velocity vector we have considered into the x direction, the magnetic flux density B bar we have considered into the y direction. So velocity of the electron we have taken into the x direction, and the magnetic flux density we have taken into the z direction. So because of these particular directions, the resultant direction of the force exerted, we can be expressing the magnitude, it will be E into V into capital B, and for denotion of the direction here we take the help of AY cap. AY cap is the unit vector directed towards this particular force here. Now this particular force will be actually having a circular motion. It won't be affecting the velocity of moving electron, but it will be taking into the direction of y, always in a constant fashion. So if you take the diagram to the help, so in this particular diagram, at the origin, if you start, we have taken the velocity of electron into the x direction. So initially it will be directed in this particular direction. But as we are getting the force directed into the y direction, it will be a continuous try of the magnetic field to get the electron diverted towards the y. So with these continuous effects, we get a circular type of motion here. So this is the path of the electron, you can say here, and for this particular circular motion, obviously the geometry we can have expressed in this particular diagram. So there will be a radius of this particular circular. Now for determination of how actually the mathematical relationship can be given to see how exactly the radius of the circular path is there, we have to take into the account that electron is somewhat tied to the central position. So the circular path motion is occurring here. So it is actually a balance, as like we have some object tied with the thread to the center. So it will be a balance between the centripetal force and that of the centrifugal force. So in that case, the equilibrium here we take with the equation. So it will be mv square divided by r. So r is radius of the path here. So this will be equal to E into V into B here. So from the above equation, we can write r is equal to mv divided by E into capital B. So as it is the radius of the path, it is a distance, the unit of measurement should be in terms of meters here. So r radius of the path we have given. Along with the path is not a straight path, it is a circular path. So for the circular path we have the cyclotron angular frequency also, so that we can denote with the help of symbol, that is omega. So omega will be actually a ratio V divided by R. So we can have the substitution of final formulation, it will be capital B along with the small e divided by m. So the cyclotron angular frequency will be having the mks unit here, that will be of radians per second here. So this also I outline. Now just now we have formulated the cyclotron angular frequency. You people very well know that the relationship between the frequency and the time period. So for the circular path there will be a time period. So the time period can be denoted by capital T. So capital T can also be expressed here in mathematical form. So for 2 pi phase of rotation here, it will be having the angular frequency omega. Hence 2 pi upon omega will give us the value of T here. Hence finally we can write 2 pi small m divided by E into capital P. So as time period for MK system, seconds will be the measurement unit here. So up till now, for the electron motion in the presence of magnetic field, we have given two sets of equations, three equations each, one into the rectangular coordinate system and another into the cylindrical coordinate system, expressing the acceleration components into the xyz and rho phi z directions here. Along with, for the circular type of motion, we have expressed with the help of one diagram, and the radius of that particular circular path has also been formulated along with the angular frequency and the time period. By the next lecture, we shall see the electron motion in the presence of electromagnetic field. So in the last video and this particular video, we have taken electric and magnetic field separately. So it will be a combined electromagnetic field into the next topic. So let us see that topic. I thank all of you for watching this particular video. For getting the more details of the subject and some another information, you can subscribe to Ekeeda channel. Thank you.